Hello friends, myself Dharmin Patel, Assistant Professor in Mathematics, LJ Institute of Engineering and Technology, Ahmedabad. This is the second lecture of Laplace transformation. In previous lecture of Laplace transformation, we studied the definition of Laplace transformation and some conditions of existence of Laplace transformation. Now, in this lecture, we discuss about some formula-based examples and first shifting property and their examples of Laplace transformation. First of all, what is a Laplace transformation? We revise it. Laplace transformation is a transformation, the one function of t converted into the function of s by improper integration 0 to infinity e raised to minus st ft dt. After we apply the integration on ft, then we get the some function of s. Now we can prove some formulas of Laplace transformation. Here we can see the some formulas of Laplace transformation. All the formulas derived by definitions of Laplace transformation. Laplace transformation is integration 0 to infinity e raised to minus st ft dt. If we replace ft by these functions, then we get some function of s which are formula of Laplace transformation. First of all, what is the Laplace transformation of 1? Laplace transformation of 1 is 1 by s. It is also obtained by the definition of the Laplace transformation. It is very z. Similarly, Laplace transformation of k is k by s. Laplace transformation of e raised to at is one upon s minus a. Laplace transformation of e raised to minus at is 1 upon s plus a. Laplace transformation of b raised to t is 1 upon s minus log b. Here we convert the b raised to t exponential function into the e base exponential function like this. B raised to t equal to e raised to log bt. T come over outside, then we get e raised to t times log b. Now we know the Laplace transformation of e raised to at, so it will be 1 upon s minus a. Therefore here a is replaced by log b, so Laplace of b raised to t is 1 upon s minus log b. Similarly, Laplace transformation of b raised to at is 1 upon s minus a log b. Now Laplace transformation of cos hyperbolic at is equal to Laplace of e raised to at plus e raised to minus at upon 2. We know the Laplace cos hyperbolic at is e raised to at plus e raised to minus at by 2. Now we apply the linear property of the Laplace transformation, so 1 by 2 come over outside, and Laplace of e raised to at plus Laplace of e raised to minus at. We know the Laplace of e raised to at is 1 upon s minus a, and Laplace of e raised to minus at is s 1 upon s plus a. Now by applying these formulas, we can find the Laplace transformation of cos hyperbolic at. Laplace of cos hyperbolic at is finally s upon s square minus a square. Similarly, Laplace of sin hyperbolic at is equal to Laplace of e raised to at minus e raised to minus at by 2. 1 by 2 come over outside, and we apply the Laplace of e raised to at and e raised to minus at. Then we get finally answer as a Laplace of sin hyperbolic at equal to a upon a square minus a square. Now, Laplace of cos at is obtained by definition of the Laplace transformation, which is Laplace of cos at equal to integration 0 to infinity e raised to minus st into cos at dt, and solving this integration we get Laplace of cos at equal to s upon s square plus a square. Laplace of sin at equal to a upon s square plus a square, which is also obtained by definition of the Laplace transformation. So all the Laplace of these transcendental functions, one constant k, e raised to at, e raised to minus at, e raised to bt, b raised to t, b raised to at, cos hyperbolic, sin hyperbolic, cos at and sin at, all are obtained by definitions of Laplace transformation. Now, this is a very important formula. Laplace of t raised to n is gamma of n plus 1 upon s raised to n plus 1. We studied the gamma function. So here I am giving the some properties of gamma function. Gamma function is gamma of n equal to 0 to infinity e raised to minus x, x raised to n minus 1 dx. Here n is positive number. Gamma of n equal to n minus 1 factorial if n is positive integer. If n is not positive integer, that means n is fractional number, then gamma of n equal to n minus 1 of gamma n minus 1. These are the some basic properties of the gamma function, and we can apply in the Laplace examples. Now we know the gamma of 1 by 2 is root pi. Now Laplace of t raised to n is gamma of n plus 1 upon s raised to n plus 1. If n does not belongs to n fraction number, then we can't remove the gamma function. But Laplace of t raised to n is equal to n factorial if n belongs to n. Both formulas are actually same, but we can write factorial form when n is positive integer. So in the second example, we can write Laplace of t raised to n equal to n factorial upon n raised to s raised to n plus 1. But in the previous form, when n is not integer, then we can't write gamma of n plus 1 is in the factorial form. Now we check the some similar types of examples related to this formula. Let us see first example. Find the Laplace transformation of ft where ft is e raised to minus 3t cos hyperbolic 2t minus sin 5t plus root t. Here Laplace transformation of ft can be written like this: Laplace of e raised to minus 3t plus cos hyperbolic 2t minus sin 5t plus root t. We apply the linear property of the Laplace, so Laplace of ft can be written like this: Laplace of ft equal to Laplace of e raised to minus 3t plus Laplace of cos hyperbolic 2t minus Laplace of sin 5t plus Laplace of root t. Here we separate the Laplace in each terms. Now we apply the Laplace of each function. We know the Laplace of e raised to 3t minus 3t is 1 upon s plus 3. So here Laplace of e raised to 3t is 1 upon s plus 3. The Laplace of cos hyperbolic at is s upon s square minus a square. So Laplace of cos is s upon s square minus 4, where a equal to 2. So its square is 4. Now Laplace of sin t is a upon s square plus a square. Therefore Laplace of sin 5t is 5 upon s square plus 25, and Laplace of root t, that means Laplace of t raised to 1 by 2 is gamma 3 by 2 upon s raised to 3 by 2. We are applying Laplace of t raised to n equal to gamma of n plus 1 upon s raised to n plus 1. Here n is in the fraction form, so we cannot convert into the factorial form. But we can apply this property to a gamma function. Now we simplify each term. In the first term we can't simplify anything, so it is as it is. So Laplace of ft becomes 1 upon s plus 3. In the second term is as it is also, so it will be s upon s square minus 4 minus 5 upon s square plus 25. So these are as it is terms. Now gamma of 3 by 2 can be written like this: 1 by 2 gamma 1 by 2. So this term will be changed and it will be 1 by 2 into gamma 1 by 2 upon s raised to 3 by 2. Now final answer, we apply the Laplace gamma function property. Gamma of 1 by 2 is root pi. So Laplace of ft is finally 1 upon s plus 3 plus s upon s square minus 4 minus 5 upon s square plus 25 plus 1 by 2 root pi upon s raised to 3 by 2. So this is the Laplace transformation of given example. Let us see second example. It is very simple form of the Laplace transformation. Find the Laplace transformation of sin square t. Here we cannot find the directly sin square t Laplace. So first of all, to find the Laplace of sin square t, we apply the Laplace of 1 minus cos 2t by 2. It is a formula of sin square t in the trigonometric form. So Laplace of 1 by 1 minus cos t upon 2. Now we separate the terms, then we get Laplace of 1 by 2 minus Laplace of cos 2t by 2. Now 1 by 2 come over outside, then 1 by 2 into Laplace of 1 minus 1 by 2 into Laplace of cos t. We know the Laplace of cos t and Laplace of 1, so we apply this one in the examples. So 1 by 2 into Laplace of 1 is 1 by s, so it will be 1 by 2 into 1 by s, and minus Laplace of cos t is s upon s square plus 4t, so finally it will be 1 by 2 s upon s square plus 4. So after taking the 1 by 2 common, we get 1 by 2 into 1 upon s minus s upon s square plus 4. By taking the LCM we get this term, and finally our answer will be 2 upon s upon s into s square plus 4. So this is the Laplace